running away. May I spend 2 minutes on something that I haven't mentioned, maybe because of the pressure, but I think it's extremely important when we are dealing with hydrology. Namely, that you have seen the surface energy balance and that we are using a satellite image to define vegetation-related parameters and surface temperature and all these. Please note, that is an instantaneous measurement. In fact, what you get is an insight into the process in one instantaneous moment of the time. And what we are usually interested is daily evaporation. So in this surface energy balance calculations, there is an assumption, as with all these observation modeling, you have always assumptions. There is an assumption that based on this instantaneous measurement, we can upscale the measured energy-based fluxes to a daily flux. And that is based on the fact, and that was, I don't go back now, one of the parameters which were shown as a result of the SEPS calculation was the so-called evaporative fraction. With relatively stable meteorological circumstances, the ratio between potential evaporation and actual evaporation is not changing. The reason for this is that that depends on the available amount of water, and that doesn't change that much during a day. So upscaling from the satellite image taken around 10 o'clock is possible for the daily evaporation just on that basis that we assume that the flux doesn't change so much during the day. Here we in fact assume the flux does change that much, but the ratio of the potential and the actual is not changing. So practically from the forcings, from the air temperature and so on, you can calculate how this ratio is keeping stable and how much it is during the day. So this is an important thing, and I think this is also an important thing to remember. Whatever flux we are measuring with satellite images, either we take two measurements and we interpolate between that, assuming a linear process, or we use other assumptions to be able to estimate the flux, because flux is a function of time. Now, I will show you a lot of slides from a colleague of mine, mixed with some of my slides, and of course from external sources as well, related to soil moisture. Again, we are coming back to the same story. We have direct or quasi-direct measurement where the measured electromagnetic energy is related to the soil moisture. But we also use proxies because we don't have direct measurement related to soil moisture. As you could hear, the penetration depth of the microwaves in case of dry snow can be of several centimeters depending on the wavelength. We are using more or less the same microwave channels, and those have also similar or related penetration depths. Here I would like to say one thing. This penetration depth is a little bit misleading. The penetration depth in the case of passive microwave measurements is not correct. In fact, this is the depth from which we get the information. It's not going in and coming out. It is the own radiation of the surface or the top layer. And in case of microwave passive measurements, we can get information. They usually say that half of the wavelengths, from a depth of half of the wavelengths of the radiation. Others say it's a little bit less. When we are using C-band measurements, then we are talking about 2 centimeter penetration depths, but that also depends on the soil moisture content. So this is not one number depending on the wavelengths, but it depends on the soil moisture content. But definitely, when we try to use microwave measurements for defining the soil moisture, we get information only from the top few centimeters. Furthermore, we can use another trick. In the optical band, we have seen that water absorbs, and you know that when you irrigate your garden, the soil is turning darker when you are irrigating it with water. Of course, because the water absorbs. So you can use this trick also in the optical, but this is coming only from the very surface. Here we cannot even talk about penetration depths because of the wavelengths. So these methods are very inaccurate. You could also use thermal measurements, saying that when something is wet, it is of lower temperature because of the latent heat that is used for evaporation. All these measurements have been done, have been tried, are not accurate enough for practical use. So we will more concentrate on the microwave methods. But here we have again a gap between what we can measure and what we are interested in. Usually, we are not interested in the top 10 or top 2 centimeters because the real soil moisture is underneath. So in fact, what we are interested in from the practical application point of view is the so-called root zone soil moisture, what is available for the vegetation, and therefore, this cannot be deduced directly from Earth observation. Consequently, we have to use other information. We have to use other proxies, and usually this is the state of the vegetation that is used as a remote sensing-based proxy for assessing the root zone soil moisture, as well as direct modeling. And there is already one product, this SMOS product, the Soil Moisture Active Passive Satellite product of NASA, which has a so-called modeled 9-kilometer resolution, 1 meter deep soil moisture estimate. Very coarse spatial resolution, only to 1 meter depth, and with relatively little practical use. So, what is happening? In fact, we were talking a lot about active and passive sensors. Here I would like to make really just for refreshing the memories, a big distinction between radar and passive sensors, which are the radiometers. The energy that plays in these games is several orders of magnitudes different. Namely, with radar, you have a much higher radiation emitted and received than what you get from passive measurements. Therefore, with passive radiometers, you can measure the own radiation of the surface in the microwaves, but the spatial resolution will remain relatively coarse compared to radar. With radar, you can reach a spatial resolution of a few meters, while with passive measurements, the spatial resolution will not exceed, at this stage, tens of kilometers. Well, you can say, depending on what you want. should I say? Again, when you have very large spatial differences, then, okay, let's not go that far. But here, we have to see also that what we are measuring. In fact, when we are measuring the passive emitted, passively emitted microwave radiation, here you can see a figure that shows that you are measuring some direct signal from the surface that goes through a covering vegetation. If we are not in the Sahara where there is no vegetation. But you also measure the emitted energy from the canopy top, that is 2. And you also measure energy which is originated from the canopy, interacted with the soil, and reflected towards your antenna. So you measure a very complex signal, and what you measure is one value from that complex signal. And here you see a very similar structure of equation that you have seen related to ice, which has different terms. Here, I was asked to use this pointer. This refers to the emissivity, and this refers to the transmissivity of vegetation. And that is interfering with the energy coming from the soil. Here you see a term that refers to the canopy, and here the energy is coming from the canopy. And here you also see a term which is related to the surface, and still this energy is coming from the canopy. So in this structure, you see that the measurement what you have is is a complex signal. So you need to know, extra information is needed for describing the canopy surface. There are different ways of solving this problem, from the very simple statistical methods and inversion by lookup tables and neural networks of forward modeling to data assimilation. So there are many different models. If you are more interested in it, I can provide you with more detailed information, but here the logic is important, that you have one measurement with a coarse spatial resolution which contains radiation from this complex system where there are a lot of feedback processes as well. What is happening when we are using a radar? In fact, we are using, I should have mentioned this before, again, although I already said so, that not only the dielectric properties, but also the geometric properties and the geometric properties of the surface affect this complex system what we were looking at here. With radar, we can have, on the one hand, the dielectric properties of the surface affecting the backscatter of the signal, but also the surface roughness, the smoothness, plays a role. Practically, with smooth surface, you will get a specular reflection. It will have a very little component, if not zero, that goes back towards the sensor, which is in the direction of where the signal is coming from. And a large component will be reflected in a specular way away from the sensor. If you have a rough surface, then you have a quite incoherent part. You will have a reasonably equally distributed surface, depending on the roughness and depending on the geometry of the surface. And of course, you have many in between. So not only the amount of water that is in the soil will define backscatter, but the surface roughness as well. Here I would like to talk a little bit about the radar and the radar geometry, not too much, not going into too much detail, but just to give an impression that how much pre-processing is needed for getting the signal that we would like to interpret for soil moisture. We know that radars are side-looking, and with this side-looking setup, we have geometric problems occurring. You know the principle, you send a radio signal out. In fact, it's a chirp that is one which has a certain length in time, that means also in space, and which has a certain energy. And from these geometric parameters, which are related to the signal that you sent out, and the energy of the power of the signal, you will receive back something. And practically the ratio of what you sent out and what you received is that characteristic value that is expressing the interaction between the target and the electromagnetic energy. So in fact, this is the backscatter that we are dealing with. And this backscatter is the one that is affected by the characteristics of the surface. This is partly defined by the geometry, partly defined by the dielectric properties. There is one more problem, that this is coming from a certain area. So if we want to get the characteristic of that particular target, we have to know that that target is in our pixel. And then we can characterize, dividing the value by the illuminated area. Then we can get the so-called backscatter coefficient, which is really related to our target, if we have one target in the pixel. This is usually described in decibels, since here, in fact, the amplification, or what is the opposite of amplification in English? Dampening is expressed, sorry? Attenuation is expressed in decibels. But when you are dealing with radar, usually you deal with images which are created with the synthetic aperture radar setup, where you don't have a very big antenna to have a very focused beam, but you have a smaller antenna. And you have more images created with this smaller antenna, where your target is located in some of the consecutive images. From this geometric setup, you can calculate a higher resolution of the image. Two problems. One is the geometry of this whole setup, where you have topography, and the topography is resulting in so-called foreshortening, when an area looks much shorter than what is, if you are looking at the range of the radar beam. Even you can have shadows where you don't have information behind the mountains. So this geometry has to be corrected before you calculate the soil moisture. I don't know whether it is really expressing good enough, but here you show geometrically corrected and geometrically less corrected images. What is even worse, we have another problem. We don't only have one target in the pixel, Not to mention that when we decompose the synthetically decompose the image, we have different distances between that single target and the same pixel on the ground. Interferences take place. And these interferences are inherent characteristics of the signal. I wouldn't like to call it noise, but this is a characteristic of the signal that has to be somehow diminished. Since we said that the soil moisture defines the backscatter through this dielectric property, but if you have the backscatter that you measure from a certain area loaded with these interferences, then you will have very difficult situation. In reality, since we don't know each and every details what is within a pixel, we cannot deterministically calculate backwards, and we cannot invert this interference issue. So practically what you can do is filtering and averaging. Roughly speaking, there are two tricks. Either you are doing a filtering in space. Within an image, you try to remove this speckle, which is the result of the interferences, with a smoothing filter. There are different adaptive filters which are trying to keep the edges and so on, but you are filtering, removing the spatial variation of the signals and calculating an average signal. Note, this signal is proportional to the soil moisture. So we are interested in the soil moisture, but we are removing, in this sense, a noise. Only in this sense. And the other possibility is if you think that you have a relatively stable surface in time, then you could make the averaging in time between consecutive images. But I'm telling you, this is not applicable for soil moisture, because soil moisture is ready to change in a minute the moment when the rain starts. So it is not really an applicable thing. I love this picture because I have to tell you that filtering the information on the right-hand side out from the image on the left-hand side is really a big art. But here you see an image which is on the one hand loaded with speckle, and on the other hand speckle has been removed, or not removed, but speckle has been dampened quite strongly. We have plenty of radar satellites up there, and I didn't put here all the satellites. In fact, that was Rohir who was first listing them and collecting all the pictures. That's why I still keep his slide. I like these satellite pictures very much. And you see that now there are operational satellites, different kind of radar operational satellites. Here I would put Sentinel-1 to the top because of one important reason, because of the temporal resolution that you can achieve with it. Here in Europe, you can get a radar image every second, third day on overlapping areas with Sentinel-1 satellites. I'm not going into details whether it's good that we don't have a full polarimetric setup, or we don't have. We can still use Sentinel-1 for soil moisture estimates. What is the trick? The trick is, as I already said, that the actual soil moisture is proportional to the backscatter, in fact, to sigma naught. We already saw that the sigma is loaded with a lot of other problems. Surface roughness, speckle. So this simple linear relation, which is there, and if you look at this, these are measurements of soil moisture versus backscatter of test areas with different soil properties. So that's why you have a bunch of lines, but all of them show a relatively pronounced and reasonably linear relation to the backscatter. The difficulty comes again. What is this sigma naught that we are measuring? First of all, it is coming with different incidence angles, since we have a side-looking structure. And the side-looking results in changing incidence angle throughout the whole image. And as you see, this is a figure which shows that how the incidence angle is related to the simulated radar signal. Oh, sorry, go back. And there is one more problem. The same issue that we saw already with passive microwave. The signal what we get is not only coming from the surface that we are interested in. So here, this is the backscatter of the surface. But we also have backscatter of the vegetation. Not to mention that this vegetation is in fact a complex canopy. And this complex canopy results in a lot of internal scattering. And the moisture content of the canopy contributes to the information of the moisture content from the soil. And just the icing on the cake is that you don't only have the canopy backscatter, but you have scatter between canopy and the soil. So you have there also a blurred information about the moisture content of the canopy as well as the moisture content of the soil. So solving this multi-source problem is quite challenging, in spite of the fact that when you have pure bare soil, then you can see a very clear relation between the soil moisture and the backscatter. Because of this, there is no golden solution on the one hand. On the other hand, you can use the combination of the two methods, I mean passive and active remote sensing, for getting a better insight into the surface soil moisture. If you go to this global soil moisture data site of ESA, there you can see results, part of the Copernicus products. There is, in the climate change initiative, soil moisture is regularly calculated with a combined method. In fact, Wolfgang Wagner is working on it in Vienna, and his colleagues, so their group. And in this combined method, there are several tricks in it. They try to use the advantages of the passive and the active, especially for upscaling the passive coarse resolution with the help of active radar images. You can download the data from this site. We are talking about water cycle. Before I show you an example how soil moisture can be used in this sense, I would like to show you this ESA water cycle integrator. I have to tell you that I opened my eyes on it lately. I started to play with it. It's a very nice thing. In fact, you can define different parameters of the water cycle, and you can download and you can map these, you can get the maps of these parameters with the help of this water cycle integrator interface. You can select areas, you can zoom in, and then you can select certain parameters, and there are data sets loaded up there, including soil moisture data set. And just to entertain you, I downloaded this video, which unfortunately, or maybe luckily, I don't know, doesn't have any narration, but it's a very nice animation made from the data set. Was it not you who made this animation? You guys. You said that you were making animations for ESA. So this shows that how gradually, with satellite image, you can cover the globe. And then there is a timeline from the end of the 70s, from calculated monthly average soil moisture of the globe. And you can see very, very nicely how the soil moisture is changing. And now what you see is the soil moisture anomaly. In fact, the deviation from the average, long-term average soil moisture value at each pixel. And here you see on the timeline how the animation is progressing in time. And the blue areas are the areas where you have more soil moisture at that moment than average. And the red areas show where you have a deficit of soil moisture. And you can see very nicely, in fact, I don't like this 3D animation, but the color would have been enough for me. You can see, for example, the flooding in East Africa, how it was jumping out with extra moisture, as well as you will see a drought in the Amazon and different other interesting events. And here we arrive again to the fluxes. So what we see here, the soil moisture is just a state variable. But if you put this into time series and you analyze the changes of the state variable in time, you immediately come to fluxes, extra water or deficit of water. So I think it's quite attractive. I don't like this jumping extras, but otherwise it's quite attractive. Look at Australia. Okay. We were talking about water bodies. We would like to know where there is water, where there is not. One thing is soil moisture. The other is that we would like to identify what is covered with water. If we look at radar, we already said that indeed when you have a smooth surface, then you will have specular reflection. That means that you will have very low backscatter towards your sensor. When you have a rough surface with vegetation canopy, you will have much more backscatter to your sensor. There is somewhere in between vegetation flooded by water. Can you differentiate it or not? That's an issue. Now, look at, this is the Caprivi region in southern Africa. And you can see here a radar image, an ASAR image, with relatively high backscatter, and the same when it is flooded with low backscatter. That means that the flooded areas have much, much more specular reflection away from your sensor. So you can identify the floods which can be verified with an optical image. In fact, it's a Landsat image here. And in the Landsat image, in a color composite, including near infrared, you can get very nice outline of the flooded area. The same flood doesn't jump out so much when you have vegetation flooded, but still you get some differences. So here in this time series, and especially here you see that the flooded vegetation area, which is shown here on the Landsat image with this ellipse, that is somewhat different from the non-flooded areas. Here you can play a little bit with thresholding, and you can identify some flooded vegetation. Again, an example of the same region with different floods. I would say that this is a good method as long as you have a smooth surface. The moment when you have waves, and those waves are not very nicely oriented in relation to your sensor, then look at this image, a Landsat 5 image of a shoreline, which cannot be identified on a radar image simply because of the wind and the waves. The surface roughness is making much, much more backscatter towards the sensor than what you would expect if the water was smooth. So basically, when you want to make a mapping of surface water, this way or that way you are using a thresholding. Either on a radar image, because of the specular reflection, you can use a threshold for low backscattering areas and identify them as flooded areas. Or you can get optical images and calculating indices, different kinds of indices, or taking the near infrared bands, and you can use thresholding. Practically, the problem is usually with cloud cover. So when you are interested in mapping your water surfaces, that is in cloud covered periods, for example, a flood. Flood needs rainfall, and that means that you don't really see what is flooded if that is under the cloud. So then you have to use complementary methods, and that is when radar images can come in, and that is when you can use radar images for mapping the surfaces. And of course, again, you can fine-tune your method. You can use, for example, an elevation model to exclude those areas, for example, which are of larger slopes. Then you can identify flooded areas, excluding those which should be on the top of or on the slope of a mountain, which is not very much possible. For this, there is again a Copernicus product. It was released not long ago by JRC. This is the Global Surface Water and the Global Surface Water Explorer. And I show a part of Hungary not because of my patriotic, or not only because of my patriotic feelings, but because the example that I will show you after this is from this area. And I wanted to point out that if you go to this Global Surface Water Explorer, you will find surface water in this reservoir, and you will find several smaller lakes which can be characterized, for example, by water seasonality. You can see that the dark blue is related to permanent, and some lighter blue shades, which don't come out very well here, those are temporary. But there's a system that they are using, combined optical and radar method, that is not sensitive to the problem that I would like to show you as a case study now, to map inundations on agriculture area. In flatland areas where you have relatively heavy soils and you have relatively low infiltration capacity of the soils, but there is much incoming water, for example, from snowmelt or rainfall, you will get this kind of inundations, what you can see here, which are temporary inundations, excess water ponding on agriculture areas. In Hungary, where this is a large problem, being a country in the bottom of a basin, which was area created by the rivers, which shows very well on this aerial photo where you can see the old river beds coming back. These are the deeper areas. Easily you can relate this to river meanders and so on. So in these areas, this water can be there for several weeks or even more months, depending on the boundary conditions. If you look at this graph here, it shows from 1935, can you see it because of the, till 2015, I think 2016 is the last, the area that was covered in the whole country in 100,000 hectares. So in fact, just to help you, this is 600,000 hectares in the country. This is really a large area covered with this inland excess water ponding, and that is a problem for agriculture production. So monitoring this is important and interesting. The difficulty, if you want to monitor this with radar, is that you have these very nice smooth open water surfaces, sometimes mixed with the crop. If you have winter crops, for example, and this ponding occurs in February, March, or partially inundated areas, which has also a certain surface roughness. So monitoring this with radar is quite a challenge. What with a student of mine we were doing, we had two test areas, one in the northern part of Hungary, and the other, sorry, hey, come back. The other in the southern part, so this is the northern part, and this is the southern part of Hungary. These are really inundation-prone areas. We were analyzing together Sentinel-1 and Sentinel-2 images to get the inundated and the non-inundated pixels. I will not, from this flow chart, I will just concentrate on this part, the pre-processing. We already spoke about the pre-processing of radar data. I think it's not that important. But the analysis, where we looked at the Sentinel-1 data and looking at the pixel statistics of Sentinel-1 backscatter, but also we looked at optical data to define the state of vegetation, the state of crops on the area, to filter and to identify where crops are inundated. We had some different kinds of crops. So the test area, within the test area, we had different kinds of crops. This is the different locations of the different crops in the southern part. And first of all, we tried to identify whether we could integrate optical images from Landsat and Sentinel. You know that the bands are not completely identical. The sensitivity of the bands are not completely identical between the two sensors. Therefore, we had to test, but it came out quite nicely that the Sentinel-2, the NDVI calculated from Sentinel-2 correlates very nicely to the NDVI calculated from Landsat 8. Then we had to characterize somehow the canopy that is covering the inundated water, if there is any canopy. And a very simple relation between the NDVI and the height of the canopy was calculated for different crops. And these relations have still a statistical relation, have reasonably good matching. Not for all the crops. The NDVI can be directly related to that. But then, since we know that if we create the backscatter ratio between the horizontally and the vertically polarized images, then you get some information that is related to the canopy that is covering the surface. It has the very rough explanation that the canopy that is there will, the thicker the canopy is, the larger change of scattering will be, or in fact, the larger change of polarization will take place. So the polarization ratio is related to the canopy, and we were correlating the polarization ratio with the NDVI, since the NDVI is the value, is the index that represents vegetation. So we can state that there is a statistical relation between the polarization ratio and the canopy that is there on the areas. After this, we found areas where we had very long-term inundations, and on this aerial photograph you can see this area. This was an area which was really flooded, and this yellow area, which was within the same field, was not flooded by this excess water inundation during the inundated periods. And you can plot the backscatter together with the rain. Here, showing very nicely that how during the inundated area, the inundated period in the winter, the inundation occurs as low backscatter from the Sentinel-1 image. So we looked at time series, and the time series show reduced backscatter during the period when in this test area there was water covering the surface. In the yellow area, you don't see this drop of backscatter so much. A little bit backscatter drop occurs here when the precipitation was snow. But basically you have a constant backscatter, and this is on alpha-alpha. That means that here we also had vegetation during the winter. So very nicely you get from the time series analysis, you can identify that how long the inundation was in that particular pixel. Then we were verifying this with optical images. The optical images have, of course, much coarser resolution, and of course a temporal resolution, sorry. And you can see that the temporal run of the polarization ratio and the NDVI is not fitting 100% well, but it is reasonably good. So we can deduce the information about the vegetation from the radar images as well. Based on this, look at this is the northern study area where the red pixels show the temporary inundation. This is, I think the date here is sometime in, I don't know exactly what was the date of the radar image. Sorry for that. It should be somewhere in the caption. So ponding water was occurring besides the permanent waters which are masked out with the blue. If you do this at field level, you can get very detailed within field distribution, not only about where the ponding is, this is our famous ellipse, but also about the temporal distribution of the inundation. So based on the time series, we could map that which part was inundated when within the field. This has, in fact, quite high importance for the farmer himself, because in this particular region, they get money not to drain these waters because of bird life. So there is a project within which, if they maintain these temporary excess water, they get some compensation for them. For the crops that they miss. But with the different colors, you can express the different inundations. And this way, you can use Sentinel-1 images operationally for mapping these temporarily inundated areas. But there are still issues with this. One is related to incidence angle. The polarization ratio, what I was showing to you, was calculated from a roughly normalized incidence angle image. But this rough normalization is not accurate enough because the canopy thickness should be taken into account when we are normalizing it. So far, the algorithms don't take into account the canopy so directly in normalizing the incidence angle. And furthermore, the crop damage can be assessed only if the radar monitoring is also combined with a more accurate optical monitoring for looking at the amount of crop that is failed. And this is the end of the story. Questions, please.
Thanks, Zoltan. Okay, are there any questions? Yep.
Yeah, when you were showing the visualization of soil moisture variations across the planet, right?
Yeah.
You didn't seem to have any values for the Amazonia. This is because of saturation of the signal, or what is the
They
reason?
don't dare to say anything under the thick canopy.
You don't see anything.
You cannot say anything. So there is all the tropical forest zones were masked out. Not only the Amazon, but also in Africa, the equatorial zone is masked out, where the canopy is so thick that you cannot really say much.
So is there any threshold in terms of biomass or something?
You are asking something that we should check exactly what they were doing.
Okay.
I am not familiar with the details of the process.
Thank you very much. I have only a question about the relationship that you obtained between the backscattering and NDVI. That relationship was for all the herbaceous crop, or it's only for your case?
It was in case of our test areas with that particular crop.
Mm-hmm.
So here I would be very careful. This shows more the idea than a very precise algorithm. Because here we have a circle or feedback process. We normalized the backscatter, so the calculated ratio is from this normalized backscatter, but in the normalization, we didn't take into account the type of crop. So there was an overall normalization, and therefore, the ratio what you get will be different for winter wheat, and different for alfalfa, and different for maize, because maize can be already in June 2 meters high, or July 2 meters high. Why the alfalfa is still something like this. So crop by crop, we were looking at it, and I think this is something that I would like to work on further.
And only one thing, do you have an idea of some study that evaluate this relationship on woody crops, in which the planting framework?
There are publications on it. I can look up for you something.
Okay.
But in fact, this is the most pronounced. The differences are most pronounced between forest and grassland, for example.
Okay. Thank you.
Any other questions? Yep.
Thank you. Just one about the validation of the phase of validation with the in situ data. I mean, it's this phase. Which kind of area find out?
Oh, that is the nicest part of the game, I'm telling you. But you see here, that is based on drone images. So this is toy for boys. Go out. In fact, this student of mine was a girl, but she also enjoyed playing with the drone and taking images. What we were doing for the validation was twofold. What you see on the right-hand side, that is the high-precision dam, and we looked at the depressions and we looked at those areas. And what you see there, here. These are the depressions, and these depressions geometrically fall very much, coincided very much with the low backscattering pixels of the Sentinel-1 image time series. And the other was looking at the crops as well, and the failure of the crops. So we were, obviously it was possible to correlate this. To tell the truth, maybe a little bit more precise validation would be needed in terms of regional statistics. So this is at a selected field level, but I really would love to do some more validation, especially where the things are not that much pronounced. For example, where you have this mixed inundation and crops and soil within a pixel.
Thank you. And also about the chemistry and physics of the soils and this kind of...
Join us in September. I'm going with another student to this place, and we are trying to make, first of all, some measurements describing the soils and the infiltration capacity of the soils and so on. The chemistry part of it is not really my piece of cake, but there is quite some research done in what modifications in the soils are occurring under these ponding areas, because you have a long anaerobe period when a lot of changes are occurring, especially in these heavy soils.
Thank you.
Yes, okay. Yeah.
Just out of curiosity, these measurements that were shown from 1980s, they were the video that you showed, the visualization. So that data was collected for moisture, or has it been reanalyzed?
Ooh, wait a minute, wait a minute. No, those were, the very first ones were based on I think thermal images. I have to check. Let's have a look. Where is this one? In fact, if we play the video, you will see on the lower left in the lower left corner. Are you playing? Come on. No, it's not playing. Now it's playing. Come on. Now it's coming. Still, I would like to. It doesn't want me to control it. Anyway, it's not too long. The Earth is opening up. And have a look at the lower left corner. You can see that which satellite image. Here you see the source, Nimbus 7 SMMR. So this is passive microwave sensor was used for the for that part of the mapping. And then, as time flies, other satellite images are also combined. Here you see SSMI is now the sensor on which the soil moisture is based. So here you have a merger of different satellite images or different satellite sources for systematic. Here you have even more sources. As there are more satellites up there, the blending of more images was used for creating the soil moisture.
And the reliability of the data that was maybe before 1990? Or how do you correct? You correct for it, or they correct?
The same as with rainfall. Since we are talking about a spatially coarse map with tens of kilometers of pixels in many cases, validating this for soil moisture is very difficult. We had some statistics, and we published a few articles on how to validate with in situ point-like soil moisture measurements, or in fact the set with the network of soil moisture measurements, these coarse resolution soil moisture maps. I'm telling you the trends are coming back well. Usually it's very difficult to say that what is the soil moisture within a 100 square kilometers area. But the change in time was nicely fitting the change what we could observe in the in situ measurement locations.
Thank you.
Statistically.
Thank you.
Jerome has a quick comment on the Amazon question.
Yeah, concerning two extremes, the floods and the very dry area. So concerning the floods, if you want to see the water under the Amazon forest, you cannot look sideways like SAR. You see the trunks. But if you look at Nadir, then you can see the water. You can see a very high backscatter of the water. So if you want to detect the flood extent under the Amazon River, there's only Nadir-looking instruments, like, for instance, the altimeter. And the altimeter is also sensitive to backscatter, and backscatter is a function of soil moisture, and it's sensitive to soil moisture only in the very, very, very dry part. So if you want to check a very high resolution and long track soil moisture, you won't be able to do a nice movie like this, but very high resolution long track, and on the driest semi-arid or arid part. You can also see a dependency between soil moisture and backscatter of the altimeter.
Okay, thanks a lot. So,
just one little addition to this, that in fact, the very first publication that I saw in '92, I think, was coming from one of the FAO guys who was mapping inundated forest in the Amazon with radar, but only where the trees were standing not that close to each other. So you are fully right.
With the trunks, sometimes you have a double echo. You get the trunks, then the water, then they go back. But
And that is so
if
intensive
they're
that
very
it
close
is-
to each other, you get just trunks. And if you want to look between the branches, through the leaves, you need the altimeter. You get a perfect link, and you get the range. I mean, you get the backscatter, which is extremely bright compared to when there's no water.
okay, I think we'll need to leave further questions to maybe the lunch break.